In the previous couple of videos, you learned about two things. First, we learned how you can use the molar mass of a compound to go back and forth between the grams of a substance and the moles. And then the second thing we learned about was how you can use Avogadro's number to relate the number of atoms or molecules to the number of moles. Now in this video, we're going to put all of those things together and expand it even further so that we can go, say, all the way from the grams of a substance and figure out how many atoms of the substance there are, or vice versa. We could start with a certain number of atoms and figure out how many grams or even pounds of a substance we had. So let's start out with an everyday question here, something not chemistry related. I find that when I give students a food-related problem, they have no trouble doing it. But as soon as it's a chemistry question, oh, everybody freaks out. So let's start out with a food question, and then I'll show you a chemistry problem that's essentially the same thing. Now, to do this question, we're going to need some information. So the first thing I'll tell you is how much a pack of cookies weighs. That there are 2 pounds of cookies in every package. You'll also need to know how many cookies are in each package, which happens to be 40. And finally, you need to know how many chips there are in every Chips Ahoy chocolate chip cookie. And when their advertisements came out back in the 60s, when they first introduced Chips Ahoy cookies, they always promised 16 chips in every cookie. I never counted them, but we'll just use that number for now. So with this information, we need to come up with a unit plan to solve the problem. So within a unit plan, first we need to know our starting and ending point. So our starting point is going to be the 1 ton of cookies, and we want to figure out how many chocolate chips there are. So our unit plan is going to start with tons. It's going to end with chips. The first thing we need to do is change tons into pounds because our cookie packages are weighed in pounds, not in tons. Once we get to pounds, we can use that first conversion to change the pounds of cookies into packages. Then we can use our second conversion to go from packages to cookies. And finally, our last conversion, we can go from cookies to individual chocolate chips. So let's see how that would work out. We'd start out with our 1 ton, and then 2,000 pounds per ton would get us to pounds. 1 package for every 2 pounds of cookies, 40 cookies in each package, and finally 16 chips in every Chips Ahoy chocolate chip cookie would give us a total of 640,000 chips. That is a lot of chocolate chips. All right, now let's try a chemistry-related problem that's set up essentially the same as our cookie problem, and I'll show you how everyday questions like our cookie problem are really no different than our chemistry problem. So don't overthink the chemistry problem. Just because you see words like molecules and moles, don't let that scare you. It's really no different than using cookies or chocolate chips. So this time, let's see if we can figure out how many atoms there are in a 5-pound bag of sugar, which is sucrose C12H22O11. Now you're going to need to know a few things about this as well, just like we did with the cookies. First of all, you need to know the molar mass of the sugar. So as we learned in the previous video, if we add up the mass of all these atoms, so each mole of carbon weighs 12 grams, each hydrogen is 1, each oxygen is 16 grams. If you add that all together, we come up with a molar mass of 342 grams. Now, the cookie example had a similar conversion. Think of the package in the cookies as being like a mole. A package is a group of cookies. A mole is a group of molecules. And each group weighs a certain amount. A mole of sugar weighs 342 grams. A package of cookies weighs 2 pounds. So the next thing we'll need is to know how many items are in our group. So in a mole, the number of items in the group is always Avogadro's number. So there's 6.02 times 10 to the 23rd molecules in a mole group. In the cookies, we had the same kind of thing. We already decided that a package in the cookies is sort of like our mole. The way the package of cookies contains a specific number of cookies, our mole package contains a specific number of molecules. And finally, we need to know how many atoms are in our molecule, and we get that by simply adding up the subscripts. We have 12 atoms of carbon, 22 atoms of hydrogen, and 11 of oxygen, and that adds up to a total of 45 atoms. And that, of course, is very similar to our conversion between cookies and chocolate chips. That one cookie, the cookie is like our molecule. It's the individual unit of the cookies. So same way that one cookie contains 16 chips, one molecule contained 45 atoms. So with this information, let's see if we can come up with a unit plan. So using these three conversions, we can formulate a unit plan. Like all unit plans, it needs to start out with the beginning and ending point. So if we look at the problem, we're starting out with pounds, and we want to figure out how many atoms there are. So our unit plan is going to have a starting point of pounds and an ending point of atoms. Well, of course, compounds are not measured in pounds, they're measured in grams. So the first thing we'll want to do is change the pounds to grams, because grams is the mass we commonly use in chemistry. Once we have the grams, we'll be able to relate grams to moles. And once we have moles, we can relate the moles of sugar to molecules. And of course, we can then relate molecules to atoms because we know how many atoms are in each molecule. So this is the unit plan we want to use for our problem. And this is the result we would get. We'd start out with our 5 pounds, convert that to grams, then using the molar mass of sucrose, we can figure out how many moles we have. Avogadro's number will tell us how many molecules in all of those moles. And finally, knowing the number of atoms in each molecule will tell us how many atoms we have total. All right, now let's compare the sugar problem we just did with the cookie problem we did a couple of minutes ago. You'll be able to see that each of the problems has basically the same setup. In the cookie problem, we started with tons. In the sugar, we started with pounds. We started with a unit of weight in each case. With the cookies, we converted the tons into the more convenient unit of pounds. For the sugar, we took pounds and converted to the more convenient unit of grams. For cookies, we wanted to figure out how many packages there were. For the sugar, how many moles there were. In the cookies, we needed to know how many individual cookies we had. For the sugar, how many individual molecules we had. And finally, in the cookies, we wanted to know how many chips were actually in each of those individual cookies and how many atoms were in each of those individual sugar molecules. So basically, it's the same problem, only the wording and the numbers are different, but try not to let that scare you. There are a few variations on the basic unit plan for doing these kinds of problems. If we're using a covalent compound like sugar, the one we just did, then our unit plan is going to be grams to moles to molecules to atoms. Now, if we have an ionic compound, there will be one change. Ionic compounds, remember, do not consist of molecules. A molecule is a covalent compound. So with ionic compounds, we use formula unit. Otherwise, it's the same. It's simply grams to moles to formula units to atoms, but the basic setup is still the same. If you have an element, it's actually a little bit simpler even, because we can leave out a step. Since there are no molecules or formula units with an element, it's simply grams to moles to atoms. So let's try a few practice problems using each one of these. All right, how many atoms are there in 15.7 grams of sodium hydroxide? Well, sodium hydroxide is an ionic compound, and therefore we're going to want to use formula units. So our basic unit plan will be grams to moles to formula units to atoms. So we'll start out with our 15.7 grams. We can figure out the molar mass of sodium hydroxide by adding up the mass of the three elements, so that would be 40 grams per mole. And as always, there's Avogadro's number of formula units per mole. And since there's 1, 2, 3 atoms in the formula, there will be 3 atoms per formula unit, and that gives us our answer of 7.09 times 10 to the 23rd atoms. The second problem involves a covalent compound, and we're actually going to do this one in reverse. Remember, any unit plan can be used forward or reverse. So this time we're starting with atoms and working our way back to grams. So our basic unit plan this time will go atoms to molecules to moles to grams. That's just the opposite. The sugar example went grams, moles, molecules, and atoms. So we start with our atoms, and then if we look at the formula, there are 11 atoms in the molecule, so 1 molecule to 11 atoms. And as always, Avogadro's number of anything, including molecules, in each mole. And if you add up the mass of 3 moles of carbon and 8 moles of hydrogen, that comes out to be 44 grams per mole and gives us our answer of 23.5 grams. Our third example deals with an element. So now we're talking about just gold, which means the unit plan that we use in this case will not have molecules or formula units. We're just going to go grams to moles and directly to atoms. The only difference in this one, the only thing I can really do to make these a little more challenging is to put a starting unit that's not grams. So I started you with ounces. We have to get to grams, so we go from ounces to pounds to grams, and then we can convert grams into moles and moles into atoms. So we'll start out with our ounces and then convert that into pounds, and then pounds into grams using our conversions from Chapter 1. Since we're dealing with gold, if you look on the periodic table, gold has a molar mass of 197 grams. And of course, since gold's an element, there are Avogadro's number of atoms in each mole, and that gives us our answer 2.21 times 10 to the 23rd atoms. So be sure to read the chapter, read Chapter 9, and work on the next worksheet, which has more practice problems for this type of question.